from this example, when we revisited worksheet 1C for a cow member that have 25 kips in compression, if we cut through a blanket that form an angle theta 30 degrees from the traverse, we have both normal and shear stress. So from that, we have a new concept that we are going to talk, and will be the last concept we talk in today's lesson. So that will be the state of stress. So let's redraw that member HI. We have here from angle theta, and with the force 25 kips, and the cut with the angle 30 degrees in there, 30 degrees. Then we have the normal stress equal to 4.69 KSI compression. So we have the normal stress sigma equal to 4.69 KSI in compression. So it gets into the cut. And the tau, the shear stress, is parallel to the cut face. And in that case, the tau equal to 2.71 KSI. So what we can talk about the state of stress. Basically, we can uniquely define the state of stress at a point by determining both sigma and tau on the two orthogonal planes. So two orthogonal planes, we already have one plane that have sigma equal to 4.69 KSI and tau equal to 2.71. If we get another plane that orthogonal or perpendicular to that plane, then we can form a state of stress. So let me write the definition first before we make that cut. So we can uniquely define the state of stress. Define the state of stress. So we can say that the SOS, right? SOS is something negative in the society, but here it's nothing to do with that. It's about the mechanics of material. At a point by determining both normal stress sigma and shear stress tau on two orthogonal axes. Planes, orthogonal planes. Two orthogonal that analyze. So two that have perpendicular. So as you can see, the angle theta for the first plane is 30 degrees. Then if we form another plane that orthogonal to that plane, then we can basically define the state of the stress of that point. So let's continue. Draw that cut in orthogonal to that plane. So here, similarly, it will be the force 25 kips again, but instead of make the cut 30 degrees to the right as shown in there, we can make an angle theta is 60 degrees in this case. And as you can see, the original 30 degrees for the cut original in that example above, and the 60 degree that to the left. So basically from the trapezius counterclockwise 60 degree, 30 degree in this case clockwise from the transverse cut, then they will form an orthogonal axis. Why is that? If I show that one here 30 degree there, then as you can see, it will be orthogonal in here, perpendicular. So from that, we can go ahead to determine the sigma and tau in that cut. So the sigma, what is the sigma in here, and what is the tau in that scenario. What is the tau in that scenario? So we can just apply the normal and shear stress equation above. So let's talk about the normal and shear stress equation that we already learned previously. In here, for any random cut theta, sigma equal to p over 80 cosine theta square, and tau equal to p over 80 sine theta and cosine theta. So let's write down here. So now the theta is 60 degrees, so you can have sigma equal to p over 80 cosine square theta, and in that case we have it 25 over 4 cosine 60 degrees square, and from that we can have 6 for just cut equal to 1.56 ksi, and still in compression. And similarly, we can have the tau equal to p over the transverse areas T80, and then sine theta cosine theta, and we plug with the theta equal to 60 degrees, so we have it 25 ksi for loss p 80 equal to 4 inch square, and then sine 60 degree cosine 60 degree. From that we can have tau equal to 2.71 ksi, and from that there we have tau and sigma for the other plane, and that plane is orthogonal to the plane that we already do previously. So from that we can have 2D stress blocks, state of stress, 2D two-dimensional stress block to represent the state of stress of that point. So if we have a block, so in this case a square with angle 30 degree and then 60 degree. Like a square, and as you can see here, that angle here 30 degree, and that one is 60 degree. So on the one is 30 degree, we already have previously here 4.69 ksi and 2.71 ksi. 2.71 ksi. So on that plane we can have the normal stress is 4.69 ksi, and then the shear stress and the shear stress 4.79 ksi, and the shear stress going down 2.71 ksi for the plane that form an angle theta equal to 30 degree from the traverse. And of course, by the equilibrium on the opposite side, we also have 4.69 ksi, and the traverse, to make it equilibrium, it go up 2.71 ksi. And on the angle 30 degrees, 60 degree, counterclockwise from the transverse, we also have the normal force in compression 1.56 KSI, and the tau is 2.71 KSI. Tau 2.71 KSI. And opposite, do the same to make it equilibrium, 1.56 KSI, and the tau is going down and parallel to that cut, and that tau equal to 2.71 KSI, and that we call a state of stress block. And as you can see, because the body in equilibrium, this block also in equilibrium. If you sum up all the force in any direction, that sum will be equal to 0. So with that, we conclude for the lesson today. And for the works, the final works is 1F that have vary the theta. So we can do that in Excel with the two equations we already determined. Sigma equal to P over AT cosine square theta, and tau equal to P over AT sine theta cosine theta.